Our presentation today is on reversing climate change through geological carbon sequestration. Carbon dioxide is a very powerful greenhouse gas that has been contributing greatly to pollution around the world as a side effect of the burning of fossil fuels for energy. Research suggests that a useful containment method of supercritical carbon dioxide, which has both liquid and gaseous properties, is to inject it into a hydrodynamic setting with several different variables in order to properly trap it and diffuse it. Although this method is very efficient, it is still young, and as such it is both expensive and has little research and improvement upon itself. Our presentation today is focused on explaining the different forms and variables of supercritical carbon dioxide sequestration and injection, and analyzing its impacts both on the economy and on the environment. Now I'll pass it to my partner to explain exactly what carbon sequestration is.
We all know that carbon dioxide is a greenhouse gas, and greenhouse gases, which traps the reflected infrared radiation, will contribute to global warming. It is estimated that if unregulated, there will be an increase in carbon dioxide emissions by 130% in 2050, causing significant temperature increase. Therefore, reducing carbon dioxide gases in the atmosphere is of utmost importance. So currently, carbon sequestration, which is the process of capturing and storing atmospheric carbon dioxide, is one of the most promising strategies to reduce carbon dioxide emissions. Why? This is because it still allows the continued use of fossil fuels and will not compromise the security of electricity supply. More importantly, carbon sequestration could be supported by current technology. There are two major types of carbon sequestration. First, biological, and second, geological sequestration. Biological carbon sequestration involves nature, such as vegetation, soils, etc., to store atmospheric carbon. Geological carbon sequestration, on the other hand, which is our main focus today, is the process of storing carbon dioxide in underground geologic formations. In order to be considered effective, the carbon dioxide must be stored underground for a minimum of 1,000 years, with a leakage rate of less than 0.1% each year. There are four main methods for the sequestration of carbon dioxide. The first is known as residual trapping. As the diagram on the right suggests, carbon dioxide is first injected underground into the reservoir. Upon injection, carbon dioxide gas will be forced downwards and displace the brine, which is concentrated solution of salt, upwards. However, as carbon dioxide has a lower density, it will eventually migrate upwards. Now, before I go any further in explaining the mechanism, I would like to introduce an important term here, wettability. It is the tendency of one fluid to spread on or adhere to a solid surface in the presence of other immiscible fluids. In this case, the fluids are brine and carbon dioxide. Now, let's shift our focus back to residual trapping. Since brine is the wetting phase, meaning that it is able to preferentially diffuse across the pores before the non-wetting phase, carbon dioxide, it coats the pore space as it migrates downwards, essentially trapping the carbon dioxide gas in small clusters of pores. This is well illustrated in the diagram, where the white space is carbon dioxide gas, trapped by a coating of brine. Now we shall move on to the second method, hydrodynamic trapping. For this method, the carbon dioxide is being trapped underground by a layer of low permeability cap rock. It's not hard to deduce from here that this method depends highly on the sealing capacity of the cap rock, which is why site selection is going to be a big challenge. Besides that, there are also a number of factors that will affect the storage capacity. First and foremost will be the buoyancy force exerted by the carbon dioxide, and it should not exceed the capillary entry pressure of the pore spaces. Second factor will be the volume of pore space and reservoir permeability. As we can see from here, the structure of the sedimentary basin will largely determine the storage capacity of carbon dioxide. And it turns out that trapping efficiency will be affected as well. So here are the two main traps for hydrodynamic trapping. The left hand side is a structural trap, which has a characteristic anticlinal folds right here, and sealed fault blocks. The other one is a stratigraphy trap, which we can clearly see layers of rocks stacking on top of one another. Now for the structural trap right here, you can clearly see there's a leak here, as carbon dioxide will be able to leak through the reservoirs to the surface. I'll now pass on to my group mate to talk about the last two methods of trapping.
Thank you. Solubility trapping is a method of trapping with specific emphasis on the water itself. You may notice it looks a bit similar to residual trapping, although rather than the carbon floating into pores for storage, it sinks to the bottom of a water supply. Supercritical CO2 is injected into the trapping, in which it is now part of a convection mechanism, diffusing into the water at a slow but not inconsequential rate. Then, it sinks, as the brine is heavier than the pure water, which pushes more water to the top and gives more space for more CO2 to be injected and stored. This causes decreased capstone migration, as most of the CO2 is sinking through the water rather than moving through the capstone itself. Mineral trapping is similar to solubility trapping, but rather than emphasis being placed on the water, emphasis is placed on the brine created. The water is preemptively mixed with different alkaline buffers, not CO2, making it easier and faster for the CO2 to diffuse in the water. However, this causes a slower and overall less effective convection method, and reduces the total amount of CO2 able to be stored in the capstone. Overall, compared to the solubility method, the capstone migration is less due to the quicker diffusion rate, but due to the slower convection rate and the greater mass of the pre-existing alkaline buffers, there's a lower capacity to store CO2. This method also has different effects for wet and dry supercritical CO2. Wet CO2, or CO2 with a lot of water evaporated into it, has different responses to different alkalinities because of the water inside of it. For this reason, mineral trapping isn't quite as universal and requires a bit more work overall. The EPA guidelines on injection and carbon sequestration are a bit complex. First off, the EPA outsources the storage and management of the CO2. There are many different places to store CO2 across the country, and the EPA has given different regions to different companies, which themselves manage and handle the CO2. However, research is done by the EPA itself, which is then passed on to the companies so the EPA can understand how to improve methods of storage and to expand and make more efficient specific methods. The EPA also has a branch of support systems in place to improve carbon sequestration circumstances all around the globe, rather than just in the USA, so other companies and governments can understand the environmental impact and look for help, both materially and intellectually, with sequestering carbon dioxide. Finally, the economic impact of carbon sequestration is very drastic. The estimated cost of storage of carbon dioxide per ton is about $80 million. This is because CO2 is a very volatile substance in terms of waste, as compared with the $320,000 per ton cost of nuclear waste. The EPA budget in 2020 was about $9 billion, which is down a fraction of a percent from what it was in the 1970s and 80s. However, this is still an increase in comparison to less recent years in between. Although the EPA has less money from the government, it has space in the budget for carbon sequestration. However, because this method is so cost ineffective, it would be better in the future to move away from fossil fuels as a whole and towards nuclear or other green methods which produce far less waste. It is important to note that greenhouse gases are running rampant, and according to EPA estimates may become far worse in the future. Luckily, the EPA has indicated that geological sequestration is a viable method, possibly the only one, for mass storage of carbon dioxide. There are 4 main methods of storage, often used in tandem so as to effectively store the CO2 and reduce leakage as according to the EPA's success guidelines, that is, less than 0.1% leakage in 1,000 years. However, for the future, the EPA is looking for greener sources of energy as a whole due to the incredible cost of carbon sequestration. Whether or not geological sequestration is viable, while it may be our current only method of storage of CO2, it is imperative we look to other methods of producing energy so as to reduce CO2 emissions in the first place. Here are our sources and works cited. Pause if you would like to see.